Remark. Observe that when we studied open ball with the discrete metric, we computed the ball center 2 and radius 1/4 with respect to the discrete metric, and we got that this is the singleton 2. Now, we just finished computing the open ball again with center 2 and radius 1/4. But now we change the metric to the absolute value, and this gave us 7/4, 9/4, this interval. So the lesson we pick from here is that the nature of an open ball we compute depends on the metric we use. The same parameter to the center, radius 1/4, radius 1/4. But we have different sets. What accounted for this difference is the metric we used here and the metric we used here. So you have to bear in mind that anytime you compute an open ball, the nature of the set you obtain at the end of the day is guided by the metric you are using. So that is very important for us to highlight, and that's what we did here. I'm going to take another example also. With different metric, keeping the same parameters, center 2, radius 1/4, and then we still see a different nature or a different set, so to speak, from what we have here. Still take this example. We take x, d2 to be the set of the set R2 together with A2. From the previous video, when we were giving examples of metrics, we saw that we defined it rather on x cross x into R by D2 of x comma y is summation I from 1 to 2 absolute value of xi minus yi squared all raised to the power of 1/2, where here our capital X is R2. Okay. This is the set. This then x0 belongs to R2, no doubt, because the first component is 0, the second component is also 0. So this is the origin, so to speak. Yeah. Now, we also take R to be 1. Our goal is this: compute the open ball with center x0 and radius 1. So we want to compute this ball. By definition, B x01 is the collection of all u in capital X, our x is R2, such that D2 of u, x0 is strictly smaller than 1. Good. We know who D2 is. Please don't forget, u belongs to R2 means that u has the form u1, u2, where u1 is a real number and u2 is also a real number. So with this information, we will be able to see what we're doing here as that this is equal to u in R2, such that summation, absolute value of ui minus Let me abuse notation and write this as x naught I squared raised to the power 1 over 2 is smaller than 1. I from 1 to 2. So when I is 1, I have u1 minus x naught 1. But my x naught 1 is 0. When I is 2, I have u2 minus x naught 2. X naught 2 is also 0. So this is nothing but all u in R2 such that absolute value of u1 minus 0 squared plus absolute value of u2 minus 0 squared all raised to the power 1 over 2 is strictly less than 1. This is what we have. Now, 1 minus 0 is, u1 minus 0 is u1, similar, we have u2 here. And so this gives us all u in R2 such that absolute value of u1 squared plus absolute value of u2 squared is strictly less than 1. Here I've taken the square of both sides. So if I square both sides here, 1 over 2 will go, and then if I square 1, I still get 1. Therefore, this is the same thing as this. This is the same as all u in R2 such that, look, absolute value of u1 squared is the same thing as u1 squared plus the other one is also same as u2 squared. This is strictly smaller than 1. So this means that the ball with center 0, 0, which is what I call x naught, and radius 1, is precisely this set u in R2 such that u1 squared plus u2 squared is less than 1. This set is precisely the inside of the circle with center 0, 0 and radius 1. If you're familiar with what is it called, coordinate geometry, you understand that this is what it is. Which, if I sketch this set, we have a shape of this form. This is 1. This is negative 1. This is 1 here. This is negative 1. So this is precisely the set of interest. So inside here constitutes the ball with center 0, 0 and radius 1. That is what it is.